classical mechanics, we do Hamiltonian mechanics. And it's one of those things at the end where it's like, what is the point? And the point is really to build for later. But so let's just do an example because there's something I really want to show you. And I'm going to use a rather trivial example of projectile motion. And I want to solve projectile motion using Hamiltonian mechanics. And we're going to make some cool plots. And we're going to show you what something cool. It's just going to be fun. Let's just do it. Okay. So the projectile motion problem I have an object moving in 2 dimensions. And with Hamiltonian mechanics and with Lagrangian mechanics, we need to say how many degrees of freedom. So I'll just say degrees right there, question mark. And the answer is 2, right? I need 2 pieces of information to tell me where this is at any point. So my 2 degrees, I could pick anything. I could use polar coordinates. Actually, that might be kind of fun. Hamiltonian mechanics with polar coordinates. But I'm not going to do that. But I want to. But I'm not going to. Not now. I'm going to pick the variables x and y to describe this. So I have an x and y position. And it's moving at some angle, so it's going to have an x and y momentum. But how do we do Hamiltonian mechanics? Well, in general, the general Hamiltonian is defined as the sum over your generalized coordinates I, pi, the momentum, qi dot, and remember we take dots to mean derivative, that's the derivative with respect to time, minus the Lagrangian. So you got 2 things you have to deal with here. First, what's the Lagrangian? And second, what's the momentum? And we could write momentum in mass times velocity, but I don't want to do that just yet. So let's start off with Lagrangian. If I have this object moving, I want to write the Lagrangian. And remember, the Lagrangian is kinetic energy minus potential. So I need to find the kinetic energy. It's trivial in Cartesian coordinates. It's 1/2 m x dot squared plus y dot squared. The potential energy is pretty easy. It's gravitational potential, mgy. So L is going to be 1/2 m x dot squared plus y dot squared minus the potential minus mgy. That's my Lagrangian. Okay, so I need to get, I have 2 coordinates, x and y, right? So I need px, x dot, py, y dot. But I need to find p. So how do I find p? Well, if you know the Lagrangian, you can find the momentum. And we call this the generalized momentum because it might not actually be momentum. So momentum, p, in general, pi, is going to be equal to the partial of L with respect to qi dot. So let's find px. It's going to be the partial of L with respect to x dot. So if I look over here at my Lagrangian, I have only one x dot. I have 1/2 m x dot squared. If I take the partial with respect to x dot, I get 2 times 1/2 m x dot squared, which is mx dot. And you're like, whoa, that's really surprising because that's mass times velocity in the x direction. What a surprise. No, it's not a surprise. It's called practice, and that's fine. Next, py is the partial of L with respect to y dot. So again, it's the same thing. It's 1/2 m y dot squared. So when I bring the 2 down, I just get m y dot. So now I have px and py, and that's important up here. Now we can go ahead and write the Hamiltonian. I'm actually going to get, I have 2 terms here. These are a sum of 2 terms, right? I have to do px x dot plus py y dot. So let's write it right here. H is, I'm just going to write it as in terms of p's first. P x dot plus p y dot minus the kinetic energy, minus the Lagrangian, which is minus 1/2 m x dot squared minus 1/2 m y dot squared plus mgy. Now you'll see that I have a problem here because I want to get the Hamiltonian in terms of p's and x's. I don't want to have x dot in there because the Hamiltonian equations depend on p and x. And I can find p dot and x dot from the Hamiltonian equations. So right here I have a px and an x dot, but I can use my equation right here and I can solve for x dot. So x dot is actually equal to px over m, y dot is equal to py over m. And if I substitute that in, I get h equals px, which is times x dot. So, but x dot is p. So I get px squared over m plus, this is going to be py times y dot, which is py squared over m. That's an x. Py squared over m minus 1/2 m x. Now again, I need to put in my x dot. So it's going to be p squared over m squared. Px squared over m squared minus 1/2 m py squared y over m squared plus mgy. And you know, I know what you're thinking. This is silly. You're just making a bunch of work. You don't need to do work. And we are doing something that's easy in the right way. So when we get to more complicated things, we can do it the same way. Now right here I have a px squared over m, and this is actually, that cancels. This is minus p squared over 2m. So if I add those two together, I get, I can add these two terms together. So let's write that Hamiltonian. H is going to be px squared over 2m. And then I'm going to do the same thing for y. I have a p squared over m, and I have a minus p squared over m. So I get py 1/2 py squared over 2m, and then I get plus mgy. And that's my Hamiltonian. Now, you will notice that in this case, the Hamiltonian is the total energy, because this is 1/2 p squared over m. I mean, p squared over 2m is 1/2 mv squared. This is 1/2 m x dot squared. This is 1/2 m y dot squared, which is the kinetic energy. So we're back to the kinetic energy. And this is the potential. So I actually get kinetic plus potential. So in this case, it is the total energy. Okay. So now we have H. We have, let me just go ahead and write down my P, just because we might need this later. X dot is Px over m. Y dot is Py over m. Now we can use the Hamiltonian equations. Hamilton's equations, there's two of them. And they say this, they're a differential equation. In general, it says Qi dot is the partial of H with respect to Pi. And Pi dot is negative the partial of H with respect to Qi. So I actually have four equations, right? Because I have I have the x1, x, 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 and I have the y's. So let's do the x's first. So this says Qi in the x direction is just going to be x dot. X dot is equal to the partial of H with respect to Px. So if I take the partial with respect to Px, the only place Px appears is right here. So I get the 2 comes down, I get Px over m. And again, that seems dumb, right? Because I just said that. Next, I'm going to find, let's do this one. Px dot is going to be negative the partial of x with respect to x. There is no x, right? So it's 0. There's no x in there. So those are my x equation of motions. So this says that the x changes with p, and this says that px is constant, which we actually already knew, right? Because if px dot is 0, then px equals a constant. And we could actually solve this. I could actually solve both of these differential equations, right? I can, px is equal to a constant. I can use that over here and solve for x by integrating both sides. I'm not going to do that right now because we know the equations of motion for projectile motion. Let's do the same. Let's do the next part up here for the y direction. So in this case, y dot is the partial of h with respect to py. Again, there's only one py, so I get py over m, and duh, we already knew that. But now I get py dot is negative the partial of h with respect to y, so it's going to be negative mg. So I have my differential equations. I have two sets of them, two first-order differential equations. But in this case, there's something really important. Only depends on x, and px only depends on y and py. So I don't have to treat these two as combined equations. I can treat them completely separately. And in fact, this is boring. This is not boring. So how would we solve a motion like this with, say it was more complicated? And we're going to do it anyway, because even though it's not complicated. Because now we have, instead of a second-order differential equation, we have two first-order differential equations. Well, the first thing that we're going to do is to, suppose I want to break this into small time steps. So let's say delta t is 0.01 seconds. And during that, I can assume that p dot is constant. So if p dot is constant, py dot, that's going to be equal to the change in p with respect to time delta t. So I can write that as p2 minus p1 over delta t. If I solve that for p2, I get p2, and I drop the y because I got bored with it, plus py dot delta t. So this says, and remember, py dot is negative mg. So this is the momentum in the y direction at the end of the time interval based on the momentum at the beginning. So if I know the starting conditions, I can keep doing this forever and find the new momentums. Now I can do the same thing for y dot. I can say y dot is constant, even though it's not. Y dot is delta y over delta t. So from this, I get y2, the position at the end of the time interval, is y1 plus y dot delta t. And how do I find y dot? It's right here. That's a y. So here's the steps. Calculate py dot. It's always the same, but let's just pretend it's not. Use that to update the momentum. Now that I know the momentum, I can use that to find y dot. Now that I know y dot, I can update y. And then I keep doing the whole thing over and over again. But you'll notice that we're calculating p and y, so this is a great opportunity. We're updating p and y to make a phase space plot. So I'm going to make a phase space plot of p versus y. I do need some numbers, so let's go ahead and pick some stuff. M is 0.1, g is 9.8, y equals 5 meters. This is kilograms, newtons per kilogram. And then p initial, I'm just going to call it p. Let's say it's 1 kilogram meter per second. And so that would be initial momentum right down here of 1. Let's call this, so maybe right there. Oh, and y is right there. And then where is it going to move? Okay. It's actually going to decrease in y value. Actually, it's going to increase in y value because it's moving in the positive y direction. But let's just go ahead and plot a motion of this, because then I want to show you something really cool. So let's jump over to Python and model this. So I'm using Python. I'm starting from scratch. Let's make a graph. Graph G1 equals graph. X title equals X. Y title equals Y. And let's do width equals 400, height equals 400. Because I'm plotting in a phase space plot, we want it to be square, even though the two coordinates aren't equal, and that's fine. And let's say F1 equals G curve, color equals color dot blue, and let's say dot equals true. I'll leave a dot. Now I'm going to put in all my initial variables. So I said y was equal to 5, p is equal to 1, m is equal to 0.1, g is 9. I blanked out there for a second. G is that. T is equal to 0. dt is equal to 0.101. Let's see. Is there anything else I need? I think I'm good. I needed my initial y, my initial momentum. Okay, that's good. So let's do this while y is greater than 0. So as long as it's above the ground, I'm starting above the ground. Let's just do it for above the ground for right now. Let's make this move in real time, right? So that way we can actually see it move. And that's what that rate statement does. So the first thing I'm going to do, like I said, I want to update momentum. So I need to calculate py dot. So p dot is equal to negative m times g. That's from my differential equations. Now I can use that to update momentum. P equals p plus p dot times dt. Now I'm going to use that p to calculate y dot. y dot is equal to p divided by m. Now I am going to update y equals y plus dy plus y dot times dt. And now I can update time, t equals t, even though I don't need to. And now I'm going to plot that point, f1 dot plot y, p, y on the horizontal axis, p on the vertical axis. Let's run it and see if it works. Oh, why did I ever do y and x? So this is, okay, what did I do? X, this is p. Okay, so we started up here. It didn't zoom out the graph, and that's fine. So we started right here at p equals 1. So it's moving in the positive y direction. And so y is going to increase. And then there's my y value of 5. So it actually, it's not a trajectory. This is not x versus y. This is a phase space plot. But you'll notice it moves up here, and then it comes down there, and it ends up right there at y is equal to 0 with some negative momentum. So that seems pretty good. Okay. Now, I'm trying to decide if I should do this. I'm going to go ahead and show you what happens if... One of the cool things about phase space is this thing called, and I'm going to pronounce it incorrectly, and someone's going to say, you're not a good person because you pronounce it. But it's the Liouville Theorem. And this says that if you have a bunch of points in phase space starting up here, the area of that those points occupy is going to be the same as down there. So let me show you that in a picture, and then I have a program already made, and I'm going to show you what that looks like. Okay, so I can't write it. This is called, and I'm not going to, I'll derive this in another video, hopefully. I'm not going to derive, because the math gets a little messy. Not too bad, but it's a little abstract, but it's still pretty cool. Liouville. You know, I work at a radio station, and I had a station manager, and he said, well, as long as you pronounce it with confidence, it doesn't matter if it's wrong or right. Okay, so that's what I'm going to do. Theorem. So let's say that I have phase space right here. And this is P, and this is Y. And suppose that I draw a box right here. And I have these are a bunch of different initial conditions. And they're going to, each one of these is going to move through time and space, and they'll end up over here. And it turns out that, I'm going to show you this in a second, the shape of these points, and they can be filled in all the way, is not going to be the same. It'll actually turn out to be a parallelogram. Like that. So here. So there's a bunch of points in here, a bunch of points, and they evolve to a bunch of points down here. But the area in phase space, which would be delta P times delta Y, is going to be the same as down here of delta P times delta Y. So well, that's not delta. I guess so. The area of parallelogram is base times height still. That's the height. But these areas are the same. So you can treat the motion of particles in phase space as though they're like a fluid, and the fluid area is conserved. And I think that's kind of cool. Okay, let me show you the program I made, and I'll walk you through it. And it's a little hacky, but I like it anyway. And I didn't want to just start from scratch, because I did some hacking. I mean, some weird stuff that probably computer science people would say you shouldn't do that and you're a bad person. But that's fine. I'm going to do it anyway. Okay, so what I did here, and actually I don't need that. I don't need that either. But it doesn't matter. So I make a graph, and then I made a function. I made a function that plots the phase space. So this function, I give it an initial y and an initial p, and then it will make a graph of that. It will make a phase space plot. This is exactly what I just did. Now there is a couple tricks here. One, I made the graph have a random color. That's fun. And I actually put a dot at the beginning and a dot at the end, just so we can see where it starts and where it ends. Then I have all my properties, mass, g, t, dt, and then this makes that first dot where it starts. And then this is my phase space plot. It's the same thing as I did, right? I calculate p dot, update p, calculate y dot, update y, and then I graph it. And that's it. And then I graph another point at the end. That's all that does. So this loop right over here, what I'm doing is I'm doing 200 phase space plots in the same graph. And so the first thing I can do is to create a random initial momentum. And this is a random momentum between 1 plus or minus 0.1. Random, right? Because this 2 times random minus 1 gives me a number between negative 1 and 1, and then I multiply by 1. So that's sort of like the same momentum, but plus or minus 0.1. And this is yt is going to be 5 plus or minus 0.4. So my box should be 0.2 long in the y direction, and then it should be 0.8 in the y direction. So it should be 0.2 times 0.8 or 0.16 should be the area. And then I plot it and I add it 1 and everything. So this is 200 points. Get ready for this. It's going to be awesome. Now I will change the values up a little bit to show you what it looks like. So isn't that cool? Let's see. There you go. So here's all my 200 points that I start off with, and they all evolve over to here to this parallelogram. But the area of this, we already said what it was, right? It's 0.16. So the area of this, let's just calculate this real quick. I'm going to write these down. I'm going to choose. Let me write these down. So this goes from the y value of 7.92 to a y value of about 8.7. And then the x value, the p value goes from 0.413 up to 0.6. Okay, so let's just print that area at the end. There's probably some cool way of actually calculating those max min points. That would be fun. But I'm not going to do that. I'm just going to do it manually. So let's just print the area. So let's say dPA for phase area. I don't know what it's called. It's going to be equal to 0.6 minus 0.413 times 8.7 parentheses 8.7 minus 7.9. Hold on. How do you? Okay. I think I put someone on hold. So let's print that. I should always pause my phone, but no one ever calls me, right? Okay, so I get 0.14, so 0.15. It's pretty close, but you can increase this number to whatever you want. So let's increase this to, let's say, 300 points. And I want to show you one more thing. That looks kind of cool. That's pretty cool. Okay, now, if the longer you let it go, it can get really hard to calculate, because watch this. If I increase this to 1.5 seconds, what's going to happen to that area? Okay, that looks cool. That just looks cool. Okay. But this is a very skinny trapezoid, and we can even let it go for a further time, but it's still the same area. Oops. Right there. Oh, look at that. That's cool. Okay, so that's, and I love these really thin lines. And I made everything a random color. It just looks great. So that's that. Phase space. We'll do some more Hamiltonian mechanics with phase space problems, but this is a good place to practice. The end. Sorry about the phone call.